Ask most people what's waiting at the edge of our solar system, and you'll get some version of the same answer. Nothing. Empty space. A dark that gets thinner and quieter the farther out you go, until there's nothing left to measure at all. That answer is almost completely wrong. In 2013, the plasma wave instrument on Voyager 1, the most distant object humanity has ever built, sent back a reading that shouldn't have been possible. The region it had just entered wasn't emptier than the space behind it. It was measurably, inexplicably denser. Not thinner, not quieter, denser. That sound is real data from Voyager's plasma wave instrument, translated into something the human ear can register. Exactly when it was recorded is one thing this video will answer, and in the years since, it hasn't gotten any less strange. A hum with no confirmed source. A density that keeps climbing when every model said it should level off. A magnetic field behaving in ways nobody built a model to predict. NASA calls all of it real, documented, peer-reviewed. Nobody calls it explained. This is the story of what Voyager 1 found on the other side of everything humanity has ever measured directly, and why, more than a decade later, the people who built it still can't tell you exactly what's out there. There is a moment in every launch before anyone knows whether it worked. The engines ignite, the ground shakes, the tower releases. For roughly 3 seconds, the rocket is close enough to the pad that failure and catastrophe are the same event. On September 5, 1977, nothing failed. Voyager 1 cleared the tower, arced east over the Atlantic, and slid into a transfer orbit toward Jupiter. The mission had a 5-year design life. The targets were 2 planets. Photograph the gas giants, study their moons, measure their magnetic fields, and then go quiet, drifting outward as its power source cooled towards silence. That was the entire plan. Ed Stone didn't expect it to last this long either. He became the mission's chief scientist in 1972, before launch, when Voyager was still blueprints and budget hearings. He held that position for the next 52 years, through Jupiter, through Saturn, through the outer planets, through a spacecraft outliving its own funding cycle 3 times over, until his death in 2024. He spent more of his life waiting on Voyager's data than not waiting on it. By 1980, the 5-year probe had already done everything asked of it. It photographed Jupiter's Great Red Spot in detail no Earth telescope could match. It found active volcanoes on Io, the first confirmed volcanic activity anywhere beyond Earth. It threaded Saturn's ring plane and found moons nobody had catalogued. And then it kept going, not because anyone commanded it to, because there was nothing left to stop it. No retro-rocket, no atmosphere, no plan for an ending. Just 17 kilometers of momentum every second, carrying it toward a region no human instrument had ever sampled directly. But distance alone doesn't explain what made this mission strange. What made it strange was the weight. Here is a fact that gets stranger the longer you sit with it. Picture sending a single message to Voyager 1 right now. It leaves Earth at the fastest speed anything in this universe is permitted to travel. The speed of light itself, with nothing to slow it down. It still takes over 22 hours just to arrive. Send a text tonight, and the reply won't land until the day after tomorrow. The response takes another 22 hours to come back. A single question, a single answer, with the most distant object humanity has ever built. Nearly 2 days, door to door. Which means everything Voyager 1 has ever told us about interstellar space is already history by the time we read it. We are not watching it explore in real time. We are reading a diary, one entry at a time, always 44 hours behind the moment it was written. 2 instruments are still writing that diary. The plasma wave subsystem, which listens to oscillations in ionized gas and converts them into sound. The magnetometer, which tracks the direction and strength of magnetic fields. In deep space, the difference between knowing where you are and being blind. There was a third instrument, the cosmic ray detector, which spent decades counting high-energy particles from beyond the solar system. NASA shut it down in February 2025. The power simply wasn't there to keep it running. 2 instruments, 1 spacecraft, 24 billion kilometers of silence in between each sentence. There is a second probe out there, Voyager 2. You'll hear about it, but it cannot see what Voyager 1 sees, not from where it sits. Before any of what these 2 instruments recorded will make sense, you need to understand what Voyager was walking into, and, more importantly, what was already waiting on the other side. And what it found there didn't match a single model built to predict it. Our sun does not simply sit in space. It exhales, constantly, in every direction. A stream of charged particles moving at 400 to 800 kilometers per second. Fast enough, at the upper end, to cross the entire continental United States in under 6 seconds. Scientists call it the solar wind, and it doesn't stop at Earth, or Mars, or Jupiter, or Neptune. It pushes outward until it can't anymore. To place the distances involved, Earth orbits at 1 astronomical unit from the Sun. Pluto, at its farthest, reaches about 50. Voyager crossed both of those decades ago, but the true boundary of the Sun's influence, the point where the solar wind finally loses its shoving match with the interstellar medium filling the space between star systems, sits at roughly 120 astronomical units out, already more than twice Pluto's distance, already past every world we've ever named. That boundary is called the heliopause. Everything inside it is, in a real physical sense, ours. Our star's magnetic field, our star's plasma, our star's shield against the harshest radiation the galaxy produces. Everything past it belongs to something else entirely. Every model built before Voyager reached it predicted a clean crossing, a sharp line where solar plasma ended and interstellar plasma began, where the magnetic field would rotate cleanly into its new orientation, where cosmic ray counts would jump and hold. The models were wrong. In the years leading up to the crossing, the cosmic ray detector began registering something odd. Not a steady climb as Voyager approached, but a fluctuation, counts rising, then falling, then rising again, as though Voyager were drifting in and out of different pockets of plasma, as though the boundary itself were breathing. Think of the heliopause less like a wall and more like the surface tension on a bubble pressed from both sides. Solar wind pushing out, interstellar pressure pushing in, the surface itself shivering under the disagreement. The magnetometer told a related story. Instead of gradually rotating as expected, the sun's field ran almost parallel to the boundary itself, as though something on the far side were imposing its own structure inward, in a way no pre-mission model anticipated. The actual crossing wasn't a single instant. But between late 2012 and early 2013, all 3 instruments, including the cosmic ray detector that would later go dark, independently confirmed the same thing. Voyager 1 was in interstellar space. Voyager was 120 astronomical units out when it crossed. It has been traveling deeper into interstellar space every year since, and sits considerably farther out today. The plasma outside the boundary was 40 times denser than the plasma inside it. Not twice, not 10 times. 40 times denser is the difference between the air you're breathing right now and the crush of a sold-out stadium packed shoulder to shoulder. That's the jump this plasma made in a single crossing. This was not empty space. This was a structured medium with mass and pressure and behavior. And its behavior was already, measurably nothing like the models Voyager had been built to test. And with that single crossing, everything scientists thought they understood about the edge of our solar system changed. But even the heliopause isn't the actual edge, not the one that matters gravitationally. Out past it, at somewhere around 1,000 astronomical units, lies the inner edge of the Oort cloud, the vast shell of icy debris that marks where the sun's gravity, not its plasma, finally lets go. At its current speed, Voyager won't reach even that inner edge for another 300 years. And the outer edge of that cloud, the true boundary of the solar system by any strict definition, sits closer to 100,000 astronomical units out. Voyager won't cross beyond that for another 30,000 years. Voyager 1 left the Sun's light behind in 2012. It is nowhere close to leaving the Sun's grip. That was the first reading from beyond our star's plasma. It was not the strangest one. Years pass. Voyager moves deeper into interstellar space, further from anywhere the models had ever described from direct measurement. Then, in 2017, the plasma wave subsystem starts picking up something new. Not a burst, not a spike traceable to a solar shockwave, a hum. Continuous, faint, sitting in a narrow specific frequency band, what physicists call narrowband emission. In physics, a signal that sustains itself this cleanly usually means something is actively driving it. The person who noticed it was Stella Koch-Ocker, a doctoral student at Cornell, combing through years of faint plasma wave data, looking for exactly this kind of pattern buried in the noise. She later told reporters the signal was so faint and steady, it barely registered as a signal at all. More like a single unbroken note held in a room that should have been silent. By 2021, Ocker and her colleagues had tracked the signal long enough and far enough to publish it in Nature Astronomy. They described a persistent plasma wave emission, detectable since 2017, continuing without interruption. The first steadily sampled measurement of interstellar plasma density ever taken across nearly 10 astronomical units of a spacecraft's journey. 10 astronomical units is roughly 1.5 billion kilometers, the same signal, sustained, unbroken, across a stretch of space that would swallow the distance from the Sun to Saturn twice over. The paper offered two candidate mechanisms: thermally excited plasma oscillations and a phenomenon called quasi-thermal noise, well documented elsewhere in the solar system. But the authors were honest about what neither explanation cleanly covered: a signal this steady, sustained this long, across a distance this large. In their own conclusion, they wrote that the true source could only be clarified by new data from Voyager, or from a future interstellar mission. No such mission exists. There are only the two Voyagers, and as you'll hear, having two probes has never meant having two answers. The hum kept transmitting, and what it detected next contradicted something even more fundamental. The standard model of the interstellar medium assumed something relatively uniform, a density jump at the heliopause, yes, expected and accounted for, followed by a quiet, consistent background stretching outward into the galaxy. The data said otherwise. The further Voyager traveled from the heliopause, the denser the surrounding plasma became. Instead of leveling off at the expected interstellar baseline, the readings kept rising. The medium wasn't settling, it was thickening. You would expect the opposite. Every diagram, every prediction, every intuition about empty space says that the further out you travel, the thinner things should get. Instead, the further Voyager went, the more crowded the space around it became. Some researchers pointed to a hydrogen wall, a theorized pileup of neutral interstellar hydrogen at the heliosphere's outer edge, pressed inward by the same forces shaping its boundary. The idea predates Voyager's crossing by decades, but a theorized pileup and a measured, ongoing density increase 20 astronomical units into interstellar space are two very different claims. If that's what Voyager is moving through, our solar system isn't simply a bubble floating in empty space. It's a bubble being compressed from the outside. The galaxy, quite literally, pushing back. Not a bubble drifting quietly through a calm galaxy then. A bubble under active pressure, from a direction nobody had modeled for. That alone reshaped how scientists described the boundary of our solar system. And then, in 2020, Voyager detected something that didn't fit even that revised picture. In 2020, the magnetometer registered an abrupt jump in the intensity of the magnetic field surrounding it. At almost the same moment, the plasma wave subsystem confirmed a matching rise in plasma density. Two separate instruments, one anomaly, confirmed twice over. This kind of spike had happened before. In earlier years, similar short-lived jumps traced back cleanly to coronal mass ejections, solar eruptions sending shock waves outward that eventually reached Voyager, briefly compressing the plasma around it before fading back to normal within months. The 2020 anomaly did not fade back to normal. It held through 2020 into 2021. The density and magnetic readings stayed elevated, never returning to baseline. Adam Sabo, an astrophysicist at NASA Goddard and the principal investigator for Voyager's magnetometer, had described the earlier, well-behaved spikes to Science magazine using a simple image, a piston, a single compression wave moving outward from the sun and then releasing, like a hand pressing down on a balloon and letting go. The 2020 anomaly didn't behave like a piston. The timing was wrong. The duration was wrong. Nothing about it resolved the way the models said it should. A model eventually tried to explain it. A 2025 modeling paper proposed one possible answer: global compressions tied to the sun's own activity cycle. It's plausible. But a model built on indirect data, checked against a single direct measurement from one probe, is not the same thing as an explanation. The question isn't closed, it's papered over. And before the scientific community could settle it, something else happened. The probe went quiet. The carrier signal was still coming through. Voyager was alive, still receiving commands, still executing them. It hadn't failed. It hadn't tripped an alarm or dropped into safe mode. But the data it sent back had become unreadable. A repeating pattern of ones and zeros, structured like nothing the ground stations could pass. A dial tone, arriving from the edge of everything humanity has ever reached. Suzanne Dodd had run the Voyager Interstellar mission as project manager since 2010. She had talked this spacecraft through wobbling antennas and dying thrusters before. This was different. Told by local reporters that the new signal wasn't what anyone expected, she said only that it looked like something, enough at least, to prove part of the computer was still alive in there, somewhere. To understand what her team was up against, you need to picture Voyager's onboard computers, 3 of them, built in the early 1970s, using technology that predates the microprocessor as most people understand it. Combined, they have roughly the processing power of a pocket calculator. They were built for endurance, not speed. For nearly 50 years, that had been enough. One of those 3 computers, the Flight Data Subsystem, has one job: collect the readings from every active instrument, package them into a transmittable format, and send them home. When it works, data flows. When it doesn't, the probe is present but incomprehensible. A voice with nothing coherent left to say. Something inside it had broken. For 5 months, Dodd's team worked the problem backward, one 44-hour diagnostic round trip at a time. No shortcuts existed. Just patience and a shrinking list of options. In March 2024, they found it. A single stuck bit, in a single memory chip, inside a computer built before most of the team members were born, corrupting every packet of data that happened to route through that section of memory. One damaged bit, in a 50-year-old chip, 24 billion kilometers from anyone who could touch it, had silenced the most distant object humanity has ever built. And just like that, everything changed. Not the spacecraft, but how fragile the team now understood it to be. They couldn't replace the chip, so they rewrote around it, restructuring the code to route the affected functions through undamaged memory elsewhere in the system. Testing the patch against a 1970s architecture the team still maintained, specifically for moments like this. They transmitted it into the dark. Then they waited 44 hours. On April 20, 2024, coherent data started arriving again. By June, All 4 remaining science instruments were confirmed working. The blackout was over, but it had obscured something else entirely. Before the failure began, Voyager's thrusters had fired in patterns nobody had commanded. Small, unexplained corrections, provisionally blamed on software quirks in an aging system. And the 2020 anomaly was still sitting there, exactly as strange as the day it appeared, unresolved. Here's what needs saying plainly. Every anomaly in this video is published, peer-reviewed, sitting in the journals and JPL's own release documents. NASA's own position is honest too. The probe is aging, and old hardware can sometimes mimic strange readings. Both things can be true at once. That's what makes none of this resolvable. Because here's what nobody can argue with. Voyager 2 crossed its own heliopause 6 years later, in 2018, in a completely different direction. It cannot verify the hum, the density climb, or the magnetic spike that never faded, because it was never in the same region of space to measure any of it. 2 trajectories pointing away from each other. 0 overlap on the readings that matter. If Voyager 1's numbers are strange because the hardware is failing, we can't confirm that. If they're strange because interstellar space genuinely behaves nothing like we modeled, we can't confirm that either. We simply don't know the shape of the thing standing between our solar system and the rest of the galaxy. And time now is the deciding factor. Voyager's power comes from 3 radioisotope generators, converting the heat of decaying plutonium-238 into electricity. In 1977, fresh off the assembly line, they produced roughly 470 watts. Every year since, the output has dropped by about 4 watts. Today, the probe runs on somewhere under 250 watts. Not much more than a couple of household light bulbs combined, powering the most distant object ever built by human hands. For decades, the engineering team has been managing that decline like a slow-motion triage. Heaters switched off, risking cold damage to instruments that can't be repaired. Non-essential systems shut down one by one. The cosmic ray detector went dark in February 2025 to keep the last 2 instruments alive a little longer. As of early 2026, that's what remains: the magnetometer and the plasma wave subsystem. The same 2 instruments recording every anomaly in this story. They have perhaps a year left, maybe 2 if the team is careful. The boundary it's still trying to explain lies so far out that Voyager itself won't reach the inner edge of the Oort cloud for another 300 years. The instruments will go dark decades before the spacecraft carrying them is even close to leaving the sun's grip. When the power finally drops too low, there will be no dramatic final transmission, no signal that says this is the end. The data will simply stop arriving. There is no Voyager 3 waiting in a clean room. Voyager 2 is on the identical power curve, the identical decline, heading toward the identical silence. And it was never in the right place to check any of this anyway. The only mission currently studying the edge of the solar system, the Interstellar Mapping and Acceleration Probe, does its work from near-Earth orbit. It maps the heliosphere's boundary remotely. It does not go there. It will never go beyond it. The hum, the density that won't level off, the magnetic spike from 2020 that never faded. All of it stops being actively investigated the moment Voyager's last instrument goes dark. Not because the mystery will be solved, but because the only instrument capable of listening to it will be gone. And whatever is out there, sustaining that hum, thickening that plasma, pressing a magnetic field into a shape nothing predicted, it will keep doing exactly that, whether anyone is still listening or not. So go back, now, to the sound that opened this video, and hear it differently. When Voyager's plasma instrument first registered interstellar space in late 2012, it gave scientists their first confirmation that something real was out there. That wasn't this sound. This one came later, quieter, steadier, and, in its own way, harder to explain. Voyager 1 didn't find monsters. It found that the edge of our solar system is turbulent, layered and pressed on all sides by forces the diagrams never showed. It found a boundary with structure and pressure and a signal nobody has fully accounted for. It found a medium getting denser in a direction physics said it shouldn't. And right now, with its last 2 instruments still drawing on a dwindling handful of watts, still transmitting from farther out than anything else we've ever built, it is still finding things, still asking questions nobody on this side of the heliopause knows how to answer. We built something that outlived every plan we ever made for it, and what it found waiting at the edge of everything suggests we understand that edge far less than we ever let ourselves believe. The hum is still there, the density is still rising, and somewhere out past the reach of anything else we've ever built, something is still pressing back against a boundary that was never supposed to bend, and we are running out of ways to keep listening.